Swayam Prabha. Digital India. Educated India.
Welcome to NMR spectroscopy. We did mono-substituted benzenes last time. Today we're going to look at more substituted benzenes. All right, here are a couple of examples, and let's work through them just like we did. One, find the unsaturations, and that's a good way to go. Two, look at the deltas and find a either a functional group or alkenes or benzenes. So you can kind of figure out what's in your compound just by looking at delta if you didn't have an IR. Okay, the delta values kind of indicate whether there's an electronegative group or donor group. All right, the next thing you would do is find the number of hydrogens and put together a structure using all of this information and the multiplicity. The multiplicity is only really useful for finding the number of neighbors, n. So using the formula n plus 1. Then you put together a structure. So you can try different isomers and come up with the correct isomer. So find the correct structure or isomer, because there will be several structures possible for that formula. But the exact one can only be found using the NMR, not the IR or not even the mass for the most part. It's the NMR that really pinpoints the exact overlay of the hydrogens on the carbon. The NMR would indicate the skeletal structure of the molecule, mainly the CH structure. Is it CH2, CH3, CH, and so on? All right. And so that's very important to lay out the exact isomer for the formula. So let's do the same thing here. C9H12. So the omega, which is the unsaturation, you can also call this the index of hydrogen deficiency. This would be the formula. And that would then give us over here 20 minus 12 divided by 2. That's going to be 4. Well, the possibilities are 3 double bonds and a ring, 4 double bonds, 4 rings, or any combination of rings and double bonds that would add up to 4. But if you have 3 double bonds and a ring, one possibility for that is a benzene. Okay, so the next thing you should check, if you got IHD or omega is 4 or above, check for benzenes. How would you check for benzenes on a NMR? Aromatic hydrocarbons are typically 6 to 9.5. Typically 6 to 8 would be most of them. 7.3 is just like normal benzenes. 7.32 would be where you would get a benzene, right close to your CDCl3. So you should check for that region. Do we have anything there? Yes, we do. 7 right here, you have this complex structure. So then we know for sure that that is your benzene. So we know we have a benzene for this formula just by the fact that we have 4 unsaturation of 4 and peaks around 7. So therefore, we have to build it around a benzene. What else is there for the rest of the molecule? That's when you have to look at these peaks and see this is in the alkyl region. So there's probably an alkyl side chain or side chains. Okay, we looked at mono-substituted benzenes. Let's look at these. All right, so let's see. Let's tabulate the data just like we've done before, which makes it simpler. A, and this is your A that's blown up here. And your A is at 1.2. And this is actually blown up here, and it is, as you can see, a very symmetric triplet. How do we know it's a triplet? Because we see 3 mountain peaks, and it's quite symmetric, so that's a triplet. And the next one is B, which is just a singlet. As you can see, there's no splitting, and that is going to be at 2.3 around. And then you have a very symmetric quartet here, C, which is blown up for us here, and that is a quartet because you can see there's 1, 2, 3, 4 mountain peaks, and that's a beautiful symmetric quartet at 2.6 around. Okay, so that's clearly alkyl region, and you can see from the formula there's really no oxygens, nitrogens, or things that are very electronegative to get it into the 4 and 5 delta. It's just all hydrocarbons. Now over here, this is clearly in the benzene region. You have D and E, and these are multiplets, and we will try to decipher them. And they are at, let's say, one is at 7 and one is at 7.1 around. And we try to figure out the number of hydrogens here for this. All right, so we can take our measuring tape or your ruler, and this is about 6, 6, 4, and this is about 6 and 2. So dividing by 2, that is going to give us a ratio here. This is a 1, 3, and then over here, this is going to again be 2, 3, and then a 3. So C is a 2, this is a 3, and this is a 3. Let's look for patterns next. What did we talk about when we saw molecules having certain side chains? We said methyls, third butyls would be singlets. Okay, do we have any? Yes, we do. And it's got 3 hydrogens all on the same, in the exact same environment, so chances are that's a methyl. So this is a methyl, B is a methyl, CH3. I'm going to just write this down. So let's look at the rest. So we know that this is your methyl. These 2 combined are going to be your benzene because they are in the 7 region. So that leaves us with just A and C. And let's see what that's going to be, because if A is going to be a triplet, it has to have 2 neighbors. If C is going to be a quartet, it's going to have 3 neighbors. So basically you'll have to have somebody that has got 3 hydrogens on a carbon to have 3 neighbors for this. And you need to have 2 hydrogens here to have a triplet. So these 3 here are going to be your triplet HA. And these 2 are going to be your quartet because you have 3 neighbors here. So over here, for all 3 of these, there are 2 neighbors 3 bonds away. And in alkanes, 3 bond couplings are the most important because they have a coupling constant around 6 to 8, around 7. 3 bond couplings are what you should really consider for the alkyl regions. Okay, when you get into alkenes and benzenes, we may consider more, but for alkyl regions, it's typically 3 bonds. These are all 3 bonds away from here. 2 bond couplings are typically not seen. That is, this hydrogen and this hydrogen are 2 bonds away. They don't couple. On the 3 bond coupling, you can see HA here has got neighbors would be 2. Therefore, N plus 1 would be a triplet. And that's what you're seeing here. 3 hydrogens triplet. For HC, it would be a singlet if you didn't have this. But now you have 3 neighbors, N is equal to 3. Therefore, N plus 1 is a quartet. And so that's what you're seeing here, quartet, 2 hydrogens for HC. And well, what's over here? There should be something over there because this is just got 3 bonds. Well, we have choices. We could either put a methyl or a benzene. But remember, if you put a methyl here, that's going to be identical to this. And we don't have that kind of a pattern here. This is a 2 to 3 ratio. You see? So therefore, there's not a methyl here. So chances are the one that's next to it is a benzene. Let's look at this region then and try to figure out where the methyl group is. The methyl group should be somewhere on this molecule because B would indicate 3 hydrogens here and no neighboring hydrogens here. So I'm going to put Y here. Y is going to be 0 neighbors. Therefore, when you do N plus 1 for this HB, N plus 1, that is 0 plus 1 is 1. That's your singlet, which is why you get a singlet for B. And you see that here, singlet B. So therefore, this is connected to something, and this is connected to something, and there's only one other thing here, which is benzene. So that means Y is a benzene. So there are 3 possibilities for connecting a benzene to these 2 groups. So a benzene over here has got an ethyl, which is your triplet quartet, and a methyl, which is this. Where do you put them? What are the possibilities for putting the ethyl and the methyl on the benzene ring at the same time? We could do ethyl and methyl like this, ethyl and methyl next door. We could do ethyl and methyl 1, 3, 1, 2, 3. So this could be 1, 2, which is ortho. This is 1, 3, which is meta, or it could be 1, 4, which is para. So those are the possibilities for these 2. 1, 2, 3, 4 carbons away. This is 1, 2, 3 carbons away. This is just right next door, 1, 2. Ortho, meta, or para. Those are the 3 possibilities, because if you come around and put it here, it's still going to be 1, 3. If you put it here, it's 1, 2. So those are the 3 possibilities. And this is going to tell us what the substitution pattern is. All right, so there are 3 possibilities. If you had these next to each other, this is going to be a 1-to-1 ratio. So if you had a hydrogen here and a hydrogen here, let's say this is D and E, this is going to be a 1-to-1 ratio. We don't see that. Let's look at this structure here. 1, 2, 3, that's meta substituted. So these are 2 donor groups. When you have donor groups, that let's say you have a donor here, electron donating group, EDG, they would put electron density on the ortho and para. So ortho and para would be shielded. Para, these are ortho. These would be shielded. In comparison, meta would be de-shielded. Okay, this would be your meta, and that's going to be de-shielded. Why is that? Well, let's take something that's more obvious. Let's say you have an OH group here, and let's say you have a methyl here. The OH lone pairs during resonance would go and put electron density in your ortho position. And it would put electron density in your para position. And if you go around the ring, it will again put it on your ortho. So there's no place in this compound where your electron density is accumulating on your meta. So ortho, you can see, has more electron density, is shielded. Para is more shielded. And again, ortho is more shielded, and then it's going to go up. So ortho and para are shielded when you have electron donor groups. And ethyl and methyl are electron donor groups. When you do the resonance and you pull this off, you'll have a tertiary carbocation there, which is more stable. All right. So therefore, you have a very nice meta-substituted ethyl benzene according to our data. So therefore, where is the meta for these 2 groups? This is your H meta. 1, 2, 3, and 1, 2, 3. This is your H meta. And there's only one H meta, and that's probably this, because that's the one that's more de-shielded. These are ortho, ortho to this, and para to this. So here is your H ortho, and I can put H ortho para because it's ortho to this and para to this, and H ortho para. Okay, these are going to be more shielded, and those three are what you're seeing here. These are HDs, and this is going to be H meta, which is HE. And so we kind of deciphered this, and we typically don't use the N+1 rule here just because you can have 3 bond couplings here, which is this, and 4 bond couplings here. So you can be coupled by ortho and meta. Now, para is 0 to 1 coupling constant, so unless you have a very powerful machine, let's say a 500 or 800 megahertz NMR, you may not see it. You may, if you really expand it, you may be able to see it on a 300 if it's a very pure sample and you're lucky. But typically, you would only see ortho and meta. And that's why you can see this is going to be a doublet of a doublet, because this is going to be splitting this and this. These are not the same. This is not a symmetric structure because you have ethyl and methyl. So you'll be splitting by this and splitting by this. If they were symmetric, then you can use the N+1 rule, but here it's not. So over here, the H meta is going to be, E is your H meta. And this is going to be your H ortho and para. So, well, we figured our substitution patterns, we figured out our side groups, so that the only thing that's left to do then is to confirm the structure here as a benzene that has a methyl and an ethyl. And we already talked about ethyl and methyl here. We already know that these are going to be ethyl CH3 here, and ethyl CH2 here, and this is going to be a singlet for the methyl. And we already figured this out, and so I leave you with that. This is going to be meta-ethyl toluene. All right, let's move on to this structure here. All right, let's move on to this structure here. We have some IR data, 30, 50, and 15, 60. Can we come up with a structure for this just using the IR data? Absolutely not. So all that this is telling us is that there is a phenyl hydrogen here, phenyl CH, benzene CH. And this could be a double bond. I mean, benzenes have, and it's also a little lower than a typical double bond, so it's probably conjugated. So that's all you can tell from the IR data, is that we probably have a benzene-like structure that's conjugated. Nothing like this. For that, then we look at the NMR structure. Again, let's tabulate the data. A, and it's blown up for you, is a huge doublet. Okay, like a palm tree compared to all of these. This is really big. So it must be significant. And it's at 1.2, which means it's like an alkyl region. B is 2.3, and that is a singlet. So this is a doublet, singlet. And here is our very beautiful, symmetric, let's say 1, 2, 3, 4, 5, 6, 7 mountaintops there. So that's a septet. We've only seen before in one of the structure, one of the side chains. So make sure you know what that is, 2.9. Again, guys, I hope that when I put up these structures, before I start working it, you already have a structure to compare with what I'm doing, okay? D, well, it looks kind of like a triplet, but it could be a doublet of a doublet as well, okay? So, doublet of a doublet, triplet, can't tell. We'll look at it. And it's at 7.1, which does tell us something. Well, we got to have one more thing to confirm this, and that is the IHD omega. So let's do that for this. 22 minus 14, and that is going to be 8 by 2 is 4. So there is only going to be a benzene, because we know we have a 7 and 4, so that's check benzene. Yes, we do have a benzene. All right, so we know that this is probably your benzene. So let's look at the integration. That means how many hydrogens are buried under each of these in identical environments. Grab your ruler, and here is a 8 to 2 to 6 to 12 around. So let's see, this is 8, 2, 6, 12. Divide everything by the lowest number here, and that is going to give us a 4 to 1 to 3 to 6. In the exact same environment. Well, it can be on the exact same carbon, because carbon has a maximum of 4 if it's methane. If it's in a molecule, it's a maximum of 3, a methyl. So how would you get a 6? Well, let's see. If you want to have 6 in identical environments, they're probably just like that, a dimethyl. And that's probably what that is. And we also saw from last time, whenever you have a huge doublet with a 6, we have to check for a septet if it is going to be isopropyl. All right, so 6 plus 1 is a septet for that. And 1 hydrogen here is going to split that into a doublet. So anytime you see doublet septet 6 to 1, we said that is going to be an isopropyl. Well, what about B? Singlet 3 hydrogens. Singlet 3 hydrogens can only be one thing, and that is a methyl. And that methyl doesn't have any neighbors. So here's a situation where you have something here that doesn't have any hydrogens on the next carbon, and you have an isopropyl here, and so you have these two being identical, and here's a hydrogen here because you have a septet, and you have a group here. And what do you think that group here is going to be then? Let's see what else is on the molecule. Well, these are all in your alkyl range, and we don't have any oxygens, chlorines, bromines, which is why you don't see anything in the D-shielded around 4 and plus or minus 1 region. You see everything in the alkyl, and you see 7. And we also saw this. And so putting these two pieces of information together, we can conclude that we have a benzene. So Y is probably going to be a benzene. Great. So we figured out most of our structures here, our side chains. We have an isopropyl and a methyl that's connected to a benzene. So if you have a benzene with 2 groups, then again the question arises, are they neighbors? Are they 1 apart or 2 apart? The only way to tell is to look at this. This is quite symmetric, as you can see. If it is symmetric and you don't have 2 identical groups here, well, what do you think the substitution pattern is going to be? Let's say we'll put our benzene over here. And we have, let's say, an isopropyl here. And here's your H. You have a choice of putting your methyl here, here, or here. Since methyl and isopropyl are different, you are not going to have a very symmetric structure if you put it here or here. And the NMR says it's symmetric. We'll try putting it here. So let's look at this. You have a very nice plane of symmetry here, right through the molecule, which means this can get reflected on this, which means these are the same. and these are the same, but they're different from these. So you have a peak like this, and this is kind of like that. Well, what do you think the pattern is going to be for this? Let's call this HD, and let's call this HE here. And they're probably both buried in here. There's only two types of hydrogens because of the symmetry. So this, if you take this apart, is probably going to be like this. This is also symmetric. The NMR reflects the molecular symmetry. All right, so let's look at this. These are neighbors. They can couple as doublets. And these are neighbors. They can couple as doublets because you have one neighbor. You can see that you have, when you have a para substituted, you typically have doublet of a doublet. If you have very distinct groups here, they would actually be split like this. If you have, let's say, on your benzene, X and Y, and X and Y are very different, you would see this. All right, depending on which one's donating or electron withdrawing, you would see doublet of a doublet for para. So that's what you see for para, is a doublet of a doublet. However, when you have X and Y being almost the same in electronegativity, I mean, this is just an alkyl, this is an alkyl group, then the delta difference, the difference in the shielding is very, very small. So therefore, they're almost collapsing into a single peak, but you can still see the doublet and the doublet here. So this is what you're seeing here, and this shows that it's symmetric and it's para substituted. This is going to be what you would see if X is not equal to Y in terms of electronegativity, if the X and Y are not the same. But here they're almost the same electronegativity, or in this case they're both donor groups and they're very similar alkyl groups, so they are collapsing into a peak like this. But you can see that it's a para disubstituted doublet of a doublet. All right, so that concludes our structure here. And over here, let's complete this. So here you have a doublet, therefore n plus 1 is going to be 2. Therefore, N is going to be 1. So all these 6 hydrogens have one neighbor. And over here, you have a singlet, 3 hydrogens, and that is going to be a methyl group. So singlet, that means N plus 1 is 1, N is 0. You can see there are no neighboring hydrogens here on this carbon. Over here, this is a septet, so therefore, N plus 1 is going to be 7. N is going to be 6, and that's your dimethyl. So we can safely say that six hydrogens in the same environment with one neighbor would be these 2 methyls. Those are A, CH. This B is a singlet with no neighboring hydrogen, so this is our B. And C is our septet, which with 6 neighbors, and that is our C. These 2 are going to be what you're seeing collapsed into this peak as a doublet of a doublet, which indicates symmetry and para substitution, disubstitution. So we looked at a meta substituted and a para substituted. We'll come back and do ortho substituted so you can see the pattern there as well. All right. So in conclusion, I'd like to leave you with this message. The way to succeed in doing NMR problems is to do them. Just get a book, anything from the library or online, and just keep working problems. The more you see these patterns, the quicker you'll be able to solve them. And we will see more substitution patterns to come. Stay tuned, guys. I will talk to you later. Bye.